Hello, in this video we're going to talk about the Cauchy Integral Remainder Theorem. Let me talk about first the importance of the Cauchy Integral Remainder Theorem, and then we'll state that, prove it, and then we'll see one application of that. So if you recall, last time in the last video we talked about the Lagrange remainder theorem, and we saw in some instances the Lagrange remainder theorem is not powerful enough. In other words, the Lagrange remainder theorem cannot prove things that are true. So, and the reason was the C in the Lagrange remainder theorem was something that the Lagrange remainder theorem did not give us much information. So we would like to find some another formula called the Cauchy integral remainder theorem that gives us a better understanding of the remainder. And all of these are for the purpose of proving that a function is equal to its Taylor series. Okay, so what is the Cauchy integral remainder theorem and how do we prove this? So the Cauchy integral remainder theorem tells us that if you take a neighborhood I of a real number x0 and take a natural number n and take a function that has n plus 1 derivatives and the n plus first derivative is continuous, then f of x is equal to the nth Taylor polynomial plus the remainder. So in other words, it gives us a formula for the remainder, a more direct formula. Rather than saying there is some c that satisfies this certain condition, it gives us a more explicit formula. It's a 1 over n factorial integral from x0 to x fn plus 1 of t x minus t to the power of n. So that is what it gives us. Okay, this expression is called the Cauchy integral remainder. So we will go ahead and prove this one. What we need to show is that the nth remainder is equal to the n plus first term plus the n plus first remainder. In other words, we have to take this remainder, extract the n plus first term of the Taylor polynomial, and then show that the rest of it is in fact the n plus first remainder. So we will prove this equality by induction. This by induction on n. So we're going to take the integral from x0 to x fn plus 1 of t times x minus t to the power of n dt, and we are going to extract an extra term here. Okay, so we are going to apply the integration by parts. So we will use the integration by parts theorem. One of the functions that we're going to be using is fn plus 1. So note that okay, so I forgot to prove the basis step, but the basis step is actually should be pretty straightforward. So basis step would be okay. So for n equals 1, what we get is f of x equals we can even just look at n equals 0. It is f of x0, so the first term is f of x0 plus integral from x0 to x f prime of t dt, and this follows from the first fundamental theorem. And note that f prime is in fact continuous, so we can apply the first fundamental theorem. Now inductive step. So assume this statement is true for n, and assume f is cn plus 2. So I have to take a function that has n plus 2 derivatives and whose n plus 2 derivative is continuous. Then I will have to prove that this nth remainder is equal to one more term plus n plus first remainder. So this is equal to, I will use the integration by parts. Note that g of t equals, so I will integrate this one. Integrate that one, you get minus x minus t to the power of n plus 1 divided by n plus 1. This is continuous on R. So the differentiable, I would say, I would even call it like C infinity on R. So we can apply the integration by parts. So for integration by parts, I will have to do fn plus 1 evaluated at the endpoint times this function minus x minus x to the power of n plus 1 over n plus 1 minus fn plus 1 of x naught times minus x minus x naught to the power of n plus 1 over n plus 1. And then minus integral from x naught to x times fn plus 2 of t. I will have to take the derivative of this one and integrate the other one, times minus x minus t to the power of n plus 1 over n plus 1 dt. This is equal to, so let me move the rest of it down here. So x naught to x, f of fn plus 1 of t, x minus t to the power of n dt is equal to fn. So the first term is just going to be 0 because that's just x minus x, which is 0. The second term would be fn plus 1 of x naught, x minus x naught to the power of n plus 1, and then divided by n plus 1. So that's what we get. And then minus integral, so there's a minus sign here, there's also a minus sign here, so those become a plus sign, plus integral from x naught to x, and then this is fn plus 2 of t, and then x minus t to the power of n plus 2 or n plus 1 divided by n plus 1 dt. By inductive hypothesis, f of x is equal to Pn of x plus the remainder, 1 over n factorial, integral from x naught to x, fn plus 1 of t, x minus t to the power of n dt. So this is the formula that we had. This was the inductive hypothesis. Okay, so I can use what I found and substitute that in here. So I'm going to use this and plug that in here. So this would give me Pn of x plus fn plus 1 of x naught over n plus 1 factorial. I have a 1 over n factorial times 1 over n plus 1. So that becomes 1 over n plus 1 factorial. X minus x naught to the power of n plus 1 plus, then again we can combine the 1 over n factorial and 1 over n plus 1. So I get 1 over n plus 1 factorial, integral from x naught to x, fn plus 2 of t, x minus t to the power of n plus 1 dt. And this is essentially what I wanted. Because the first portion, this portion, is Pn plus 1 of x. And the rest is the remainder that I wanted. Integral from x naught to x, fn plus 2 of t, x minus t to the power of n plus 1 dt as desired. And this completes the proof. So what I did was I showed that the next remainder can be obtained by extracting one more term of the Taylor series. Okay, so now let's look at an application. If you recall, last time I proved the natural log of 1 plus x is equal to its Taylor series, but what we did was we showed that for every x between -1/2 and 1, this equality holds. And I told you this is actually a weakness of the Lagrange remainder theorem. So here in this example, we are going to show this equality holds for all x from -1 to 1 rather than from -1/2 to 1, which means this equality holds for some things that cannot be proved using only the Lagrange remainder theorem, but it can be proved using the Cauchy mean value theorem. Okay, so let's call this one f of x. We have shown that nth derivative of f is, so we have a formula for this one. We have done this one before. -1 to the power of n plus 1, n minus 1 factorial, 1 plus x to the power of -n. So this is something we have done before. So we're going to take this and we are going to apply the Lagrange, the Cauchy mean value, Cauchy integral remainder theorem by the Cauchy integral remainder theorem. Natural log of 1 plus x is going to be equal to Pn of x plus 1 over n factorial integral from 0 to x fn plus 1 of t x minus t to the power of n dt. And this is true for all x greater than -1. So this is equal to Pn of x. Now we're going to substitute fn plus 1. Its integral from 0 to x. Fn plus 1 was -1 to the power of n plus 2 n factorial 1 plus t to the power of n plus 1 times x minus t to the power of n dt. N factorials cancel and we get Pn of x plus -1 to the power of n plus 2 integral from 0 to x, and the exponent should be negative. This one can be written as x minus t over 1 plus t to the power of n times 1 over 1 plus t dt. Now we need to show this remainder approaches 0. So we need to show for every x inside the interval -1 to 1, the expression -1 to the power of n plus 2 integral from 0 to x, x minus t over 1 plus t to the power of n, 1 over 1 plus t dt approaches 0 as n goes to infinity. So this is the thing we need to show. If you look at that expression, for every t between, so I'm going to take two cases. The first case is x is positive. So suppose x is between 0 and 1 and t is between 0 and x. If you look at the expression x minus t over 1 plus t, this is clearly greater than or equal to 0 and is less than or equal to x minus t because t is positive. So that means if I look at the x minus t over 1 plus t to the power of n times 1 over 1 plus t, it's greater than or equal to 0 and less than or equal to x minus t to the power of n, because 1 plus t is less than or equal to 1. So by monotonicity, integral from 0 to x of x minus t over 1 plus t to the power of n times 1 over 1 plus t dt is less than or equal to integral from 0 to x of x minus t to the power of n dt. Now, this guy is x minus t to the power of n plus 1 over n plus 1 negated. And we have to evaluate this at x and then subtract the value of this one at t, at t equals 0, which is the first portion is just 0, and the second portion is x to the power of n plus 1 over n plus 1. So thus, if you look at the remainder which was negative 1 to the power of n plus 2, integral from 0 to x minus t over 1 plus t to the power of n 1 over 1 plus t dt. This is going to be less than or equal to x to the power of n plus 1 over n plus 1, which is less than or equal to 1 over n plus 1. Now, since limit of 1 over n plus 1 is 0 as n approaches infinity, by comparison lemma, this remainder goes to 0. So we are done with that. So, and this is the remainder. So in the case when x is positive, the remainder approaches 0. Okay, now suppose x is between negative 1 and 0. Okay, so let me draw a diagram for this one. The fraction that we are dealing with is, so x is somewhere here. It is excluding negative 1, and t is somewhere here. The fraction is x minus t divided by 1 plus t. This is 1 plus t. So it's a ratio of these two numbers. If I look at the ratio of these two numbers, the ratio, it's a fraction that is less than 1, so something like 3/4. If I add the same quantity to both of them, so if I add that same quantity to both of them, for example, if I add 1 to both of these, I get 4/5, which gets something it becomes larger. 5/6 is even larger. 6/7 is even larger. So if I add the same quantity to both of them, to the numerator I add this quantity, I get x or minus x. To the denominator I get 1. In other words, that fraction is less than negative x, and that's enough for us to solve the problem. So we claim that for every t between x and 0, if you look at the fraction, x minus t is negative, so I will have to do t minus x over 1 plus t. This fraction is in fact less than negative x. So how do we prove this one? We are going to just do just by cross multiplying and seeing what we get. So this is equivalent to t minus x is less than negative x minus tx, which is equivalent to t plus tx less than 0, which is the same as saying t times 1 plus x is less than 0, which holds since t is negative and x is greater than negative 1. Okay, so so that means, therefore, when I look at the t minus x over 1 plus t, this is less than negative x for all t between x and 0. So I have this inequality. And by the way, it's probably better to make these closed intervals, because I want to eventually integrate both sides, and this one will be less than or equal to. So let me turn all of these into less than or equal to. Okay, so I have that. So then if you look at the remainder Rn of x, absolute value of Rn of x is equal to, so if we go back and see what we had, the negative 1 to the power of n plus 1 can be dropped, so we get integral from 0 to x. In fact, since x is smaller, I'm going to put the x at the bottom, and then t minus x to the power of over 1 plus t to the power of n, and then 1 over 1 plus t dt. So this is the absolute value of Rn of x. There's a negative 1 to the power of n plus 2 that I can drop. And that's less than or equal to integral from x to 0. This is by monotonicity. X to the power of n, negative x to the power of n, times 1 over 1 plus t. And this is easy to integrate. Integral of this is negative x to the power of n is a constant, and integral of the rest of them is natural log of 1 plus t from x to 0. So it's natural log of 1 plus 0 minus natural log of 1 plus x, which is negative x to the power of n times natural log of negative natural log of 1 plus x. Now, negative natural log of x is a constant, and negative x to the power of n approaches 0. Since negative x in absolute value is less than 1, negative x to the power of n approaches 0. So thus, by comparison lemma, Rn of x also approaches 0. And that's exactly what we wanted to show. In order to show the function is equal to its Taylor series, we would need to show its remainder approaches 0. And that brings me to the end of this video. So if you would like to continue with this topic, feel free to subscribe, and I will see you in the next video.